Hello, this is the third in the series of dynamics of rigid rotating bodies, and in this, the third and last of the series, we're going to look at gyroscopes. Before we do so, let me just remind you of two important equations that we developed at the end of the second of the series, and that was that the angular momentum vector is equal to r, the distance from the axis, cross P, where P is the momentum, and the torque on a system, the vector for torque, is equal to the distance from the axis vector, r, cross F, where F is the force. And the important point about this was that if you take, for example, the torque, if you have a force and you have the r vector, which is the distance from the axis, then the torque, because it's a cross product, will be perpendicular to the plane of these two vectors. So it will either come out of the paper or it will go into the paper. And I explained that what you do is you use the corkscrew rule. If the force is going to cause the system to twist clockwise, then the torque goes into the paper because a corkscrew would go in if it goes clockwise. And if the force would tend to turn the object anti-clockwise, then the torque comes out of the paper, because if you turn a corkscrew anti-clockwise, it comes out. So if we apply that principle to a disc, here is a disc, and it is of radius r, capital R, and I apply a force this way, so I'm going to spin this disc around this point here, that's the pivot point. Put a little pin in it, there's the pivot point. I spin it clockwise. And I do it by giving it a force F. Then this formula here will tell you what the torque will be. But the important thing is that the torque will be along the axis of rotation. And it will, since I'm going to turn this clockwise, then the torque will be into the paper. If I were to apply the force in the other direction and make it go anti-clockwise, then the torque would come out of the paper. So let's just try to demonstrate that. Here is a disc. It's actually a DVD disc. And I'm going to put it on an axis. So there we have a disc on an axis. Okay? And what we're saying is that if I spin this disc clockwise by giving a force at the edge, of course, it doesn't spin very much because there's a huge amount of friction. But what we're saying is if I spin this clockwise, then the torque and the angular momentum will go along the axis in that direction. If I spin it clockwise, it's going, as it were, into the paper. On the other hand, if I spin it anti-clockwise, the torque comes out of the paper along this axis here. So here is the disc, which I'm going to sort of draw as if it were almost end on, and there is the axis. So it's spinning like this. It has a radius r, and I'm going to apply a force such that I'm going to spin this object, as it were, this way. That is, if you're looking at it anti-clockwise, if you're looking at it from this direction, that's anti-clockwise, and consequently the torque and the angular momentum vectors will both be along the axis. And you may recall that we showed that the angular momentum is equal to the moment of inertia of the disc multiplied by omega, the angular velocity. When I give this disc a torque, apply a torque by putting a force at a distance r from the axis, that will set it going at an angular velocity. Of course, my system will slow down because there's a huge amount of friction. But if it's pretty frictionless, then once I've given it a force, it will start moving and it will continue moving forever. That's essentially Newton's first law. Now I want to take this selfsame system, we're sort of looking at the disc edge on, and here is the axis, and I'm going to spin the disc in an anti-clockwise direction, which means, as we've said, the torque vector and the angular momentum vector are going to be in this direction along the axis. But I'm now going to get hold of the axis itself, and I'm going to try and twist the axis. In the case of this axis here, I'm going to pull it towards me, or towards out of the paper. This axis I'm going to push into the paper. So again, here is my demonstration. This is the disc on the axis. And what I'm saying is that I'm going to take that part and push it downwards, and this part comes up. So effectively what I'm going to try and do is to twist the whole thing in a circle like this, except I'm not going to do the full circle. All I'm going to do is to twist it like that. Twist like that. When the disc is spinning, it's not spinning at the moment, but when it is, I'm going to spin it like that. So I'm going to give it a kind of a 45-degree twist. Now let's just think for a moment what that means. When I twist about, essentially I'm twisting about an axis in this direction, because I'm twisting, this goes down and this comes up, so it's going round an axis in that direction. I'm going to create a new torque and a new angular momentum. And since I'm going, if this is going down and this is coming up, I'm essentially going clockwise. That means there will be a torque and an angular momentum in this direction. Remind you, the torque and angular momentum in this direction are caused by the spinning wheel, or the disc. The torque and angular momentum in this direction are caused by the fact that I'm trying to rotate this entire system by twisting this axis. So we've got an angular momentum vector in this direction and an angular momentum vector in that direction. What do you do when you've got two such vectors? Well, you can add them together, and you add them tip to tail. Doesn't matter which order you do it in. So here we've got a vector L, the angular momentum vector, which is due to the spinning wheel. And here we've got an angular momentum vector, that's this one. Call this L1, call this L2. That is due to me trying to spin the entire system about an axis in this direction. And the resultant vector is just joining the tail of the first with the tip of the second. And so this we can call LR, the resultant angular momentum vector, which is pointing in this direction. So, can you see what's happening? Here is the disc, which you're looking at end on, there it is. We're looking at it end on an axis. We've got an angular momentum vector going out along that axis. When I attempt to twist it like this, I will create an angular momentum vector in that direction. And the resultant angular momentum vector is in this direction, here. So, absurdly really, when I try to do this, if this disc were spinning and it didn't have any friction, when I try to do this, what would actually happen is nature would take over and say, aha, you cannot do that. What will actually happen is you'll get a resultant angular momentum in that direction. So the minute I try to apply a torque in this direction, the disc will force my hand so that the angular momentum vector is now pointing in this direction, and the disc itself will be in that plane. It sounds absurd, and that's one of the peculiarities of a gyroscope. You think you're twisting it like that, but nature says, aha, you can't. And it twists your hand without you realising it, like that. And the reason that the disc flips to an angle of about 45 degrees, of course it would depend on what torque you apply around this axis here. But it will flip to about 45 degrees, and the reason it does so is to preserve angular momentum. Angular momentum cannot be destroyed. Of course, you can force it if you're strong enough, but then you're essentially absorbing some of the energy out of the system. And you can get gyroscopes, you can buy them about the size of a tennis ball, and it's quite good fun with your friends. If you place a gyroscope in someone's hand, and I'm not really good at drawing hands, but you know, here's someone's hand with too many fingers, and you spin it such that, say, the angular momentum vector is in this direction, and you say to them, just twist your hand, just take that tennis ball and twist it like that. What you will find, of course, is that by doing that you create a torque, and that requires the gyroscope to adjust. And so people think that they're going to turn the gyroscope like that, and they end up finding that it forces their hand to move in a direction they didn't realise. When you're holding a gyroscope and you try and move your hand, it has the most peculiar effect. If you want to see this example more clearly, I don't have the facilities to do this here, but if you Google or if you look at YouTube and simply search on gyroscopes and pick one of the films that you'll see that uses a bicycle wheel, not on the ground obviously, you have to lift the bicycle wheel off the ground, you can give a bicycle wheel a great deal of angular momentum by spinning it. It tends to be reasonably frictionless, so it keeps spinning for a long time. And then you simply try and twist the bicycle wheel. If this were a bicycle wheel, you try and twist the bicycle wheel like that, and what you will see is it will actually turn like that without you wanting it to or even realising why it does. And that, I hope, is the explanation that I've given. Incidentally, I should issue a warning: if you're going to try this yourself with your own bicycle wheel, be careful, because this is quite dangerous. There is an awful lot of energy stored in a rotating bicycle wheel. If you spin that wheel quickly by taking the drive wheel off the ground and then turning the pedals so that the wheel is rotating very fast, that is a lot of energy. And you may find yourself being, you try and turn the wheel one way using the handlebars, and the bicycle will actually tip. So be very careful if you try it yourself. Now we come to an experiment which I'm afraid I can't demonstrate. Again, you can see this on YouTube, other clips, but I'm going to explain why it happens. I'm going to take essentially a pyramid, and I'm going to take the disc on its axle, and I'm going to balance it on the pyramid like this. So here is my pyramid. It's just a pepper pot, and I'm going to balance the axis of the disc on the pepper pot and let go. What's going to happen? Well, you will tell me, of course, precisely what's going to happen. What's going to happen is that the disc will simply fall off. That's what you'd expect. But now let's suppose that I do exactly the same thing, but this time I set the disc spinning. It won't work here because, of course, the disc stops spinning almost immediately because of friction. But look up on YouTube, you'll see the example of what happens. What will happen if I set the disc spinning? You might say, it doesn't really matter. When you let go, the whole thing is going to fall down. But is that so? Let's imagine that the disc is spinning anti-clockwise. And that means that there will be an angular momentum vector, just as we showed before, along the axis and in this direction. But this whole device here, this wheel, this will have a mass. And so there will be a force, mg. If the mass of the wheel, draw better m than that, if the mass of the wheel is m, then there will be a force mg acting down, and that force will act at this distance, which we'll call r. And so you've got a torque. This is a torque, a force times a distance from the pivot point. And that torque will be R cross F, where F is the gravitational force mg. And that force will cause this axis to rotate, in theory, in a clockwise direction. In practice, of course, what we know is it simply rotates and falls off. But at least initially, it's rotating, or trying to rotate, in a clockwise direction around this pivot point. And if it's rotating in a clockwise direction, it will create a new angular momentum vector, and that angular momentum vector will be going into the paper, because it will be along the axis of this rotation. So if we look from above now, so here is our pyramid top looking from above, here is our wheel which we're looking at end on, and here is the angular momentum vector pointing in this direction. Then there will also be a new angular momentum vector, we'll call that L1, we'll call this L2, and that is caused by the attempt by the, as it were, the force, the mass of the actual wheel itself is creating a torque, and that torque creates an angular momentum vector in this direction. Consequently, if you do the usual rule of adding vectors together, you'll get a vector, a resultant vector, which we'll call LR, in this direction. And remember, we're looking overhead at this. So what we're saying is that if you do this, then the angular momentum will need to change. And in this example, we're looking overhead. Here's the pepper pot. We're looking down on it. Here is my axis sitting and the disc here. We'll pretend the disc is spinning. And what this says is that the force that is trying to create a rotation downwards will in fact create a new angular momentum pointing in this direction. And that the resultant angular momentum in this direction plus the new angular momentum in that direction will create a resultant angular momentum in that direction, which means that absurdly, instead of the wheel falling off, it simply rotates like this to the new angle. That's this angle here. So it rotates to a new angle. But look, the force is still applying, and that will create now a new torque in this direction. And so consequently, the wheel will turn again to adjust to that point. And effectively what happens is, since the force is always there, the weight of this disc is always there, the wheel will simply rotate on the top of the pepper pot. So if I explain that with this diagram, when we start out, we have angular momentum from the rotating wheel in this direction, and angular momentum from the force of the wheel acting clockwise in this direction will produce, if you look overhead, a new angular momentum vector in that direction, creating a new resultant angular momentum. But then if you look a few moments later, here it is, this is the new angular momentum vector pointing in that direction. There is still a force acting downwards, because remember we're looking from overhead, so there's a force acting downwards, and that is creating a new angular momentum vector in that direction. And that will create a resultant angular momentum in this direction. But then when the angular momentum is in that direction, there is going to be a new angular momentum created by the force, which is going to turn it like that. So consequently, the disc is just going to rotate parallel to the surface of the table around the top of the pyramid. Sometimes that is said that the angular momentum is chasing the torque, the new torque that's created by the force of the disc acting downwards, creating a torque into the paper and consequently an angular momentum vector into the paper. And so this whole system chases the torque. The torque, of course, is constantly moving, it's constantly rotating as the disc itself moves. So it's a never-ending process. And what you see is, you will not believe it when you see it. You will see something that should, by all accounts, simply fall off, and you will see it simply rotating around the top of the pyramid. And that process of rotating around the top of the pyramid, rather like this, is called precession. And we can calculate what that precession frequency will be. Let's start where the angular momentum vector was in this direction, and because of the torque applied, it's going to move to this direction. It goes through an angle delta theta, and it travels a distance which we'll call delta L. Delta L is the difference in the two vectors. Remember, to get the vectors you do them tail to tail, and then the difference is the distance between the two tips. And we'll say it travels delta L in a time delta t. So the wheel is here, essentially this is the wheel here, this is the axis, and the wheel spins because of the torque that's applied by its own weight, essentially. Now we know that delta theta is equal to delta L over L, because that's the definition of a radian. L, of course, is the magnitude of the angular momentum vector. And from that we can say that delta L is equal to L times delta theta. Now if we look at and see how that changes with time, we know that all this happened in a time delta t. That means that delta L divided by delta t is equal to L times delta theta divided by delta t. Well, the rate of change of angular momentum with time is simply the torque. The rate of change of angle with time is the angular velocity. And that is the velocity of precession, the velocity with which the gyroscope travels around the point, the angular velocity. And that means that omega p is equal to tau divided by L. Tau is the force. Sorry, tau is the torque, which is force times distance. If we go all the way back up here, we can see that the force is mg and the distance is r, that is the distance to the pivot point. So tau is mg times, and in this case, of course, we can regard that distance as L, the value or the length of the angular momentum vector, its magnitude, divided by L, which is I omega. And omega in this case is the rotation of the disk itself. So the disk is rotating with a certain frequency and the whole system is rotating with a precession frequency. This is the rotation of the disk. This is the precession frequency. And so you get that omega p, which is the speed with which the whole thing simply rotates, is equal to tau divided by L, which is mgl over I omega. If the g is of course a constant, if all these things are constant apart from mass, you can see that the precession frequency will change as the mass changes. So if you have a heavier wheel, it will rotate much faster than if you have a wheel of less mass. Finally, let me just explain some of the uses to which you can put gyroscopes. Let us suppose that we have a rotating disc on an axis, and it's, let's say, rotating anti-clockwise, and we know therefore that it has an angular momentum I pointing along the axis. And what I'm going to do is to fix a metal rod to the axis like this, connected up here, and then I'm going to have a pivot point here and a handle that comes up here that I can hold. So this is free to swivel on this particular pivot point here. Now let's say I walk about holding this point here. The angular momentum vector is pointing in that direction, and let's say I pointed in the direction of north. Now there's no torque on this system because this is a freely moving pivot point, so I'm not applying a torque in any way. When I turn a corner, this angular momentum will not change. It will continue to point north. So as I turn, if the angular momentum vector is pointing in this direction, when I'm walking, say, in this direction, the angular momentum vector, the axis of the gyroscope, will be pointing in that direction. If I turn a corner like this and I'm now walking in that direction, the gyroscope's axis will continue to point in that direction. No matter which way I turn, the gyroscope's axis must maintain the same direction because there's no torque on the system, so there can be no change in angular momentum. Not only will it continue to point in this direction, but of course it will also continue to point in the direction, if we're looking at it sideways on, it won't change like that or that either. It will always keep in this direction. So it's not only telling you the correct latitude angle, but also the correct longitude angle. And this is why it's so useful for navigation purposes. If you have a spinning gyroscope, of course you need to make sure it keeps spinning, then it will always point in the same direction no matter how much the object on which you're travelling may be twisting and turning.